Hello. Today we're going to talk about Chapter 13, From Randomness to Probability. So, a random phenomenon is exactly how it sounds. It's something we don't know when or if it'll happen. Okay? Now, here's some more vocab for you. You have a trial, which is something that we observe the random phenomenon to happen. Okay? A trial is something like the act of rolling a die, okay, or spinning a spinner. The outcome is the value of that trial. So, rolling a die and getting a 4, the outcome would be a 4. All right. The event would be when you combine outcomes. So, rolling one dice and getting a 3 and another dice and getting a 4, that's an event, okay? Or, flipping a coin, getting 2 heads. The sample space is all your possible outcomes, okay? Any possible thing that could happen, okay? Obviously, within what you're doing, you're spinning a spinner. You're not going to throw in something random, okay? Okay, so what if we don't know the outcome? Okay, so for instance, this graph is recording what happens at an intersection, so getting a green light. Okay, they don't know what the probability is of getting a green light, so they start tracking it. All right, over time, you can see that the probability settles down. Okay, and that's the law of large numbers. When you repeat it over and over and over again, and the proportion, all right, settles down. Okay, let's see. It's a lot more simple to do it if they're independent. So if one trial doesn't influence another trial, okay, make it so they're independent. So getting green lights, okay, flipping a coin. You wouldn't want to pick a marble out of a bag, not replace it, and then pick another marble. Okay, that's not independent. So, let's see. We call this empirical probability, all right, because we're observing something over time. So it's not the actual probability, like getting a head is 1/2, okay? This is over time. And here you can see over time the probabilities become more consistent. So on the first day, we recorded the probability of getting a green light. So the first 4, the green, red, purple, and orange, or yellow, people did not get a green light. Then on day 2, all right, then a couple people got green lights. That blue line is still getting green lights, okay? Then this is, cumulative over time, okay? Day 5, how many green lights did they get out of the 5 days? Okay, so yellow's not doing so hot, all right? They're getting barely anything, okay? So at the end, after day 5, it looks like their probabilities are really different, okay? So it's not consistent. However, if we track it to 20 days, we'll notice then my probability gets closer, okay? Notice the percentage is the range is a lot closer. It's from 40, a little over 40 to a little under 20. Whereas here, it went from almost, 0 to 80, okay? So then we did 500 days, and again, you can see how it evens out, okay? It's not exact, but it gets close enough, and that's what law of large numbers is. It's doing something over and over and over again and seeing if it levels off. So, a competing law is the law of averages. People say this all the time, and lo and behold, guess what? People are wrong, okay? And it's one of those things where it's, do you want to point them out and then you sound snobby? Because it happens all the time, okay? It's called the law of average. People think that, if it hasn't happened in forever, it's due to happen, okay? So it just doesn't make sense, you know, when you're betting on numbers, for instance, gambling. Oh, well, sevens haven't happened in like an hour, so they're bound to happen now. It's got to. No, it doesn't, because that's not how math works, okay? It doesn't do what you want it to do. It's the law of large numbers is a really long time. So you're watching something for forever, okay? You're trying to go as long as possible. So there's nothing that says short run, and there's no way to know what short run is defined as. You know, in theory, you can be like, oh, well, okay, if we haven't seen a 7 in 5 years, well, we're due for one. Okay, well, 5 years isn't really that short when you look at, I don't know, a century. Okay, yeah, infinitely long time. Okay, this is also a fun one. People say this with babies all the time. Oh, well, you've had 7 girls. You're bound to have a boy. It's got to happen. No. And because life is the way it is, you're more likely to have a girl, in my opinion. I mean, that's not true either, but that's what people do. They mess it up all the time. Okay? So, first thing, we start modeling probability. And some French mathematicians started it out by looking at games of chance, right? Because they wanted to gamble with their money. So they developed theoretical probability, and that's ones where we know what it's going to average out to. Like if the dice is fair, we know that over time, if we roll a bajillion times, the probability of getting a 6 is 1 out of 6. Okay? It's equally likely to get heads or tails. Over time, it should be 50-50. Right? That's theoretical probability. However, you have to keep in mind, right? Not in games of chance, right? Not all events are equally likely. Okay? Getting a 7 and getting a face card is not equally likely. Michael Jordan has better than a 50-50 chance of making that free throw. Okay? So that's not equally likely for him to miss it and get it. Okay? So understand your probability. Okay? Start with the basic. Okay? Your theoretical probability is your modeling probability. So the number of outcomes that you want to get over the possible outcomes. Okay? So the probability of drawing a face card, so know your deck of cards. It's very important that you know clubs, spades, hearts, diamonds. You know this. Okay? It's going to pop up. It's the most, I don't know how to explain it. It's the most common use of probability. Okay? So the probability of drawing a face card, a jack, queen, or king, all right, anything with a face, is what? So how we say it is probability face card equals, well, the number of face cards that are out there. This is where it gets people messed up. They go, oh, well, I want a face card. So then they go, oh, 1 out of 52 cards. That's not it. It's the number of face cards that would satisfy getting what I want. Well, to get what I want, it's all these face cards. So that is 12 cards. 12 cards will get me what I want. So it's 12 out of 52. All right? Or 3 out of 13. I get a lot of people, this is supposed to be basic probability, okay, that mess us up. They think, oh, I would just want one face card. No. I have the probability of getting one by getting, I have 12 chances here. Okay? If that's confusing, just talk to me in class. For the sake of this class, we are not going to deal with personal probability. Okay? Like, what's your probability of getting an A? Kids ask questions like this all the time. I don't know. Did you do your homework? Did you pass your tests? I don't know. You should have a good shot. But I can't give you exact numbers because there's too much uncertainty. Okay? Anyway, so for this thing, we're going to stick to formally defined probabilities. Okay, rolling dice, flipping a coin. All right, so this might come as a shock to you, but the very first 3 rules for working with probability, okay? This is very important. Make sure you write this down. First rule, make a picture. Very key, all right? I'm a visual person. You will be too. Pictures change the world, and usually we do that with Venn diagrams. Rule number 2. Oh, make a picture. Okay. Rule number 3. Oh, again, make a picture. Maybe I should make a picture. Okay. All the time I get kids that get confused with their probability and they don't have anything drawn. Okay. It's hard to visualize probability if you don't have a picture, whether that's Venn diagram, a tree diagram, something to visually see what's happening. Okay. So, we're dealing with probabilities, so not data, but same rules. Always draw a picture. It's going to save you. So, what do you need to know about formal probability? Well, rule number 1, 2 requirements. A probability is a number between 0 and 1. Okay? It doesn't really make sense to say that the probability is -4. Okay, that makes no sense. All right, a probability, think of it, another way of writing it is a percentage. Percentage can only be 0 to 100. Doesn't make sense to say -4%. Doesn't make sense to say 130% probability. So it's like gonna happen more than it's just gonna happen. That makes no sense. If 100% is it's going to happen, like 100% chance of rain, how on earth is it going to be 150% chance of rain? Like it's going to rain, but then it's really going to rain? No, that makes no sense. Okay. All right. I know Florida has different levels of rain, but come on. Okay. So the probability can be from 0 to 1. Notice it's inclusive. Okay. 0, 0%, never going to happen. 1, 100%, always going to happen. 0.5 probability means it's 50%, equally likely. Okay? Understand that. It's very important. All right? I get this all the time. If you're going to guess on probability, guess a number between 0 and 1. Okay? That's just, yeah. Okay, so probability assignment rule. The set of all outcomes must be 1. Okay? So the probability of all outcomes is 100%, meaning you've accounted for 100% of the outcomes. Okay? Usually that sample space, when we write it with a Venn diagram, it's a box, and the whole entire box represents 1. Okay, so the area of the box is 1. Okay, the complement rule is the outcomes that are not in the event. Okay, so called the complement. Okay, so usually it's denoted with an, kind of looks like an exponent with a C. The letter C, that is complement. Okay, the probability of the complement happening is 1 minus. Okay, that the complement, I said that weird. Okay, so if the probability of A, let's just say that was 0.4, then the complement of A must be 0.6. Okay, because 0.4 plus 0.6 must equal 1. The entire box is 1. So A plus its complement must equal the sample space, which is 1. Okay, hopefully that makes sense. All right, the addition rule. So, all right, when you have mutually exclusive, all right, events that don't affect each other, then if I want to know that the probability of both A and B happening is just probability of A plus the probability of B. Okay, if they're mutually exclusive or disjoint. Okay, So that's when they exclude each other and they're not going to touch each other. They're like, ew, get away. Okay, that's mutually exclusive. Okay, because they mutually agree to exclude each other. Okay, I don't know why, but it took me a while. I don't know what it is with these words. It took me a while to remember this. They're not overlapping. Okay. Okay, so again, probability of A and B. I'm sorry. That's not the right symbol. Ooh, let me fix that. Hold on. Nope, I didn't put the wrong symbol. I'm just being silly because it's late at night. So the probability that one or the other occurs is the addition rule. I know, you want to say it's and make it the addition rule because A and A, but no, that's not how that works here. So if you're doing A or B, so this is the union symbol, so that represents or, okay, so A or B, then you do probability of A plus the probability of B, but the probabilities have to be disjoint or mutually exclusive. When you say probability of A and B, that's the multiplication rule. Okay, so what are the chances of A and B happening at the same time? These events need to be independent, right? Which means that they don't affect each other. So spinning a die, rolling a dice. Okay, it is not picking a marble, not replacing, and picking another marble. You cannot use that multiplication rule here. They have to be independent. Do not assume independence. Think about it. Okay? With statistics, you always have to think about your information before you apply the math. Okay? That's what's hard about statistics. All right. The two events need to also be not mutually exclusive, so they need to overlap. Okay? All right. Okay, so why don't we practice some probability? So think about this, see if you can come up with the probability. Okay, you can either write it as a decimal or write it as a percentage. Okay, so this is what I would do. So if a car is not US made, then that means it's the complement of it being made in the US. So we do 1 minus the probability that it's made in the US, which is 0.4. So the probability that it's not made in the US should be 60%. Okay. Now a car is made in Japan or Germany. So probability that it's in Japan is 0.3. Probability of Germany is 0.1. I don't care which one, so we just add the probabilities. So we should just get 0.4 or 40%. Now you see two cars in a row from Japan. So one from Japan would be 0.3. And then you see another one. So 0.3 times 0.3, because I see a Japanese car and a Japanese car. So we multiply. So that would be, let's see, 0.09 or 9%. There we go. All right, none of the three cars came from Germany. So let's see, 10% from Germany, so that means 90% it didn't. And we want 3 cars, so we're just going to raise that to the third. So that should give us 0.729, so 72.9%. At least one of the 3 cars is US made. So the complement of at least one is the probability of none. So we're going to do 1 minus the probability of none to get this. Okay? Because at least one means I could have 1 US made, 2 US made, or 3 US made. So we're going to do 1 minus, well, the probability that none are US made is, let's see, 0.6. So 0.6, and we want 3 of them. goodness, what is that? 216, so 0.216. And then 1 minus that is, oh goodness, I hope I'm right, 784, 70, that seems awfully high. Oh, yes, perfect. Okay, oh, well, I guess that would be pretty high if you're, at least one of them had to be US made, or 2 or 3. Yeah, it should be a higher percentage. All right, then the last one. The first Japanese car is the 4th one you choose. So we want non-Japanese car, non-Japanese car, non-Japanese car, Japanese car. Okay. Alternatively, you could have written 0.7 to the 3rd times 0.3. Okay. So let's see. I did this earlier. Let's see if I can do this again. It was, hold on, 49, 243, 1029, 1029. Oh, I hope I did the math right. Yes, 10.29%. Perfect. If it doesn't make sense, ask me. Probability is one of the hardest things. All right, so just ask me. I get this is confusing and I'm not perfect. So ask me again. I can reword this and rephrase it and help you get it. Okay, so just to clarify some notation. Again, if I want A or B, we use the union. Okay, so the union is or. Probability of A and B is like this. Okay, what helps me here is I think of an A. Oh, kind of looks like an A. I know. It's silly, but you got to do what helps. Okay, so A for and. Okay, so what we just did, happening at least once, is the complement of not happening at all, and that's a whole lot easier to find. Okay, you may see some used to mean at least once. What's the probability that some of the eggs in the carton are broken? Okay, one of the eggs. Okay, because some of the eggs, right, you're just trying to get an idea. Okay. So some means at least one. Okay, so these are some obvious flaws. Okay, some surefire ways to tell that you don't know what you're talking about or they don't know what they're talking about. You got to fix it. Okay, they're big no-nos. Probabilities that don't add up to 1. Doesn't make sense. Okay, you can't have 120% probability. Don't add probabilities if they're not disjoint. Okay. So they have to be mutually exclusive for you to add them. Don't multiply them if they're not independent. Okay, so understand these. Have that memorized. Don't confuse disjoint and independence. Okay, disjoint is when the events can't occur at the same time. Okay, they don't affect, they're mutually exclusive. Independence means that one can't affect the other. Okay? All right. Big one. Probability is based on the long run relative frequencies, and I mean a very long run. Okay? Law of large numbers, long run behavior. Don't say the law of averages. That makes no sense. All right, and then you've got your basic rules. Okay? If this is confusing at all, please come talk to me. You are not alone. All right? I'll see y'all in class.